Okay, hi everyone. Hi guys and girls. Okay, for this video, it will be a replacement video for students who actually did not uh able to actually attend my classes on Tuesday. So I will say I'm sorry for the last minute class cancelling because my grandpa actually passed away due to COVID. So I still have to go back to Johor and settle the funeral and stuff. So that's why I understand my Tuesday class is actually the only day I'm having the English version class. So I'm so sorry for those who actually cannot attend the Mandarin class and other classes. So this video will be actually a replacement for you guys, hopefully. Uh, but I will just let you guys know first because this is a recorded video. Okay, so I will have no one to actually interact with. Okay, so I'll be alone at here lah. Okay, so don't worry. Okay, I will try to make this class as interesting as possible. Okay, so guys, hopefully you guys don't mind for this week lah. Okay, so I'll be back next week. Don't worry about it. Okay, so for student in Form 4, okay, so we're actually looking into your Form 4 chapter number 7. Okay, so we are officially done with Form 4 chapter 6, which is what? Which is your acid, base, and salt. If you remember, it's been a very long journey through your Form 4 chapter 6, right? You learn acid, okay, you learn base, okay, and especially when we learn salt, we learn around like 2 months, okay, one and a half months. Okay, so actually it turns out to be in total in chapter number 6, right? We actually have like 2 to 3 months of learning that chapter. So it took a long time for that. So finally, we are ending your chapter number 6. We are entering chapter number 7. And chapter number 7, I will say it's the second last chapter. So in your whole Form 4, you only have 8 chapters. So chapter number 7 is the second last chapter already. Okay, something to be glad about. Okay, so this chapter is about rate of reaction. So basically from the word here, rate, you all learn in physics. Rate means speed. Speed of what? Speed of a reaction. So for chemistry, we have to say rate of something. Because in physics, or you all always learn like rate of displacement, rate of speed. Okay, so basically rate means like the time taken for this thing to happen. Okay, so let's say for rate of reaction, it's basically the time taken for a chemical reaction to actually finish. Okay, now. So for here, you see, the meaning of rate of reaction is actually the measure of the change. Okay, the measure of the change in the quantity of reactant or product in a unit of time of the reaction. So in simple word means that how am I supposed to know how fast a reaction actually occurs? You need two information. Number one is the changes of your quantity of reactant or product. Means what? Guys, what is reactant? What is product? Reactant means before reaction. Let's say if I have a reaction, A plus B, you form C and D. So before you react them, this is known as reactant. Okay, after you react them, they turn into a product. So this is the difference between reactant and product. So basically, either way, you measure either one side, then you actually have the time taken for the reaction to actually happen. Then you can take the value, the quantity, probably like mass or maybe your volume, over the time taken, you should be able to find the rate of the reaction. So that's why you see in my formula, rate of reaction is basically the change in quantity of reactant or product. So the quantity at here is not fixed. It depends on question. Let's say if I have a reaction that release out gas, so I will collect the gas. So the gas I collect the volume of gas. I have the volume of gas, then I divide the time taken, then I know how fast is this reaction. Means in 1 second, he released how many gas, how many volume of gas, which is a very simple example I use every year. How am I supposed to know how fast can I sheet? You need two values. Number one, when the moment you start to sheet, you start your stopwatch. You calculate the total time for you to start your sheet and you end your sheet. And then number two, you have to measure the total mass of your sheet that you actually sheet out during this process. So you take the total mass of your sheet, divide the time taken, then you can know that in 1 second, how many gram of sheet do you actually sheet out? Let's say, guys, I sheeted like 5 kg of sheet, a lot. 5 kg is a lot. In 5 seconds. So what happens is you take your total of my product, okay, that's my sheet, right, my product, over the time taken, which is the 5 seconds. So means I sheet off 1 kg per second. 1 kg, 1 second, 1 kg of sheet come out. Disgusting, right? So basically, that's how I know how fast and what is the speed of me carrying out this shitting process. So of course, in your chemistry, we're not going to learn how fast we're going to shit. We're going to actually learn what? We're actually going to learn like how fast can this reaction actually occur. So in the chemical reaction, we are considering them as some is fast reaction, some is slow reaction. Okay, now, so rate of reaction is inversely proportional to the reaction time. What is the meaning of inversely proportional? Which is basically the relationship, it's inverted, it's reversed. That's why you see, if I take, imagine again, 5 kg, I take 5 seconds. The other day, I shake 5 kg, I take 10 seconds. So which one give you a faster reaction? You do your maths, 5 divide 5, you get 1. 5 divide 10, you get 0.5. Do you see the value of the first experiment is bigger than the second experiment? So basically, the number of rate of reaction is bigger. You have a faster reaction, which is by the time you also can actually predict out by logically thinking. I shit 5 seconds and I shit 10 seconds, which one faster? The shorter time, the faster reaction, right? So basically, when you see a reaction takes a shorter time to complete the reaction, then you have a faster reaction. Okay, now, so we see in conclusion, faster reaction takes a shorter time. Slow reaction takes a longer time to occur. See, combustion, okay, displacement reaction, okay, neutralization, double decomposition, your electrolysis and stuff. These are all happens in within like minutes, okay, they're within like in seconds or within minutes. But if you take a reaction that is longer than hours or even days or even years, you see, rusting, it takes weeks, right? Okay, tooth decay take months. Photosynthesis take hours. In few hours they have to actually carry out photosynthesis. Fermentation also take hours. Food decay also take days. So basically, you can see anything that is longer than that, it takes hours to go through. Then you call it slow reaction. If it takes like second, how many seconds, how many minutes, then you finish your reaction, that is considered a fast reaction. So if by going down, you can see that, see the relationship between rate of reaction and time. You can see that when the rate of reaction is high, so guys, normally when we talk about rate of reaction, we always use the word high or low. Don't use fast or slow. You can say fast reaction, you can say slow reaction, but you cannot say fast rate of reaction. You cannot say slow rate of reaction. So when you actually have the word rate, you only can use high or low. Okay, of course you can use increase or decrease. But if you try to describe, okay, you have to say high or low, not fast or slow for rate of reaction. Okay, when they have the word rate of reaction, use high or low. So high rate of reaction takes shorter time to complete, while low rate of reaction takes a longer time to complete. So we know this, okay? And we actually have a graph, guys. This chapter involves a lot of graph drawing and also a lot of graph sketching. Okay, we have to sketch a lot of graph. So draw the general graph represent the relationship between the rate of reaction and time, which is, you see this y-axis is rate of reaction, and then you see the time is here, is your x-axis. Higher rate of reaction takes a shorter time. Okay, now lower rate of reaction takes a longer time. Okay, so make sure you understand this graph here. So state the reason to know the reaction. Okay, so you see, slow down or prolong the storage of food in food industries for economy. So the reason why we're going to learn this topic is actually very useful in our daily life. Let's say for now, I know that food decay takes around like days. Then I can actually try to do some changes to even slow down the food decay process, to keep the food last longer and stuff. At the same time, let's say if I want to have a fast reaction, I want to burn something fast, I can add something to make it burn faster. So you can see use of catalysts to speed up chemical reaction for cost effectiveness. These are all the information that we can see from here. So how to measure the rate of reaction when the reaction produced is a gas? I mentioned to you, if your product is a solid, very simple, measure the mass, measure the time, take the mass over time, and that is your rate of reaction. But if your product is a gas, let's say if instead of shitting, I want to check whether how fast can I fart. Okay, solid, but the point is, if your product is a gas, how am I supposed to know the reaction is fast or slow? You have to collect the gas. So you either use any gas syringe or probably use an inverted test tube, inverted burette also can. So if you actually have a solid product, you can see that mass loss is what you're gonna actually measure. But if your product is a gas, okay, you're gonna measure the volume. collect the volume of gas. Then you can measure your real reaction. Okay. Okay. So let's say for this example here, of course, we're going to learn this more in future. But this is basically a very simple experiment here. I will mix this thing called Na2S2O3. We call it the sodium thiosulfate with hydrochloric acid. So when this thing occurs, this is the chemical equation. You see, they will form gas. Okay, you will form SO2, you will form gas, you will form solution, which is water, and the NaCl salt. But then the most important thing is the easiest thing to measure, I would say, is actually the solid. So guys, so let's say for here, in this example here, I have solution provided, I have solution produced, I have gas produced, I have solid produced. So the best way to measure the rate of reaction for this experiment is to measure the easiest thing to collect. And who is the easiest thing to collect? I would say is a solid. So when I actually check the solid, you see, because this sulfur is a yellow powder, it's a yellow precipitate. Below this conical flask, I will put a paper with this X mark here. So when I try to carry out this experiment, the moment when you form sulfur, the sulfur will cover up the X mark, because do you see the eye? You look from the top. So eventually when the sulfur is produced, the sulfur will cover up this X marks from the top view. Okay now. So and then you stop your stopwatch. You know that how long it will take to actually produce the sulfur, how long it will take to actually see for the X mark to disappear. So for here you see why SO2 is not used in your calculation, because SO2 cannot be measured because it is soluble in water. Because this gas is soluble in water, means that some part of the SO2 you never collect. You didn't collect some part of the SO2. It makes you to actually have an inaccurate result. Then your real reaction is not accurate. So the best way to have is the mass of the sulfur, okay, and then the time taken for the sulfur. Then you actually take your mass over time, you can find your rate of reaction. Okay, so for this case here, you can see that the changes can be observed and measured in different ways. Okay, I told you this, you can either look at your reactant or you can look at your product, right? But the reactant and product got one very big difference is reactant is always decreasing against time. Do you see that? The graph going down against time. Why? Because let's say for here, C plus O2 becomes CO2. If I take your C plus O2 becomes CO2, means that C and O2, they will decrease, right? Because you're using it up, becomes CO2. Therefore, CO2 increase. So you see my arrow here is reactant always drop because you are using up the reactant. But your product is always increasing because you are forming new product. You're producing new product. That's why your graph for product, starting from 0, you will always go up. But do you see the curve? It's curving, then starting in the beginning here is very steep, but eventually it turns out to be less steep and eventually becomes a straight line. Why? Because this shows that your reaction very fast at the first few minutes, then your reaction slowly gets slower. Why? It's again, I shit. Do I shit the same amount every second? No, my shit in my stomach, in my intestine finish already. Then no more shit coming out, lesser shit in my intestine, then lesser shit coming out. So that's why you see in the curve here, you see that your product is getting your curve is getting straight line, getting less curved and less steep, right? Because eventually your reaction will stop and you will stop producing product. That's why your graph eventually becomes a straight line. Okay, now same thing goes for this part here. You see, you drop. Eventually you will see your reactant actually fixed at one point. Why? Because they have two reactants here, right? Either one of it finish, then your reaction stop already. Let's say if here got 5 grams, here got 10 grams, so it means each gram of carbon will react 1 gram of oxygen to become like 1 gram of carbon dioxide. It's a very fair deal. But the thing is, because carbon only got 5 grams, oxygen got 10 grams, means that who's gonna finish first? Who's gonna get used up first? Definitely it's your carbon, right? So because your carbon used up first, means that your oxygen got left over. You get the point? That's why the graph never touched 0. The graph at here, there's a gap here because there are always some leftover, some extra reactant that you never use it up. Okay, but then the reaction stopped already. So the reaction stopped because one of the reactant finished, completely reacted. Okay, unless you say, teacher, what if I say both of them are used up at the same time? Then your graph can go down, become 0. can. Okay, but if your one of your reactant never finish, then your graph should be curve and then straight line. Again, straight line means what? Complete reaction. Okay, means your reaction stopped already. Okay, so that of course you can see from here, I mentioned to you, if you produce a solid, it's best to actually measure the mass and the time. You can take mass over time, you find the rate of reaction. If you actually have a gas as your product, you measure the you use a gas stream. Okay, for here you see that the gas stream eventually in the beginning, in the initial position, this plunger, this piston here, is supposed to be like close, okay, touching this part. But because the reaction you do here, you produce gas, the gas here will actually push the piston to the right a little bit, and then you can see this is a volume reading because this is a string. String got volume one, so you can actually get the reading out from the of the gas. Once you have the volume of gas, you have the time taken. Take volume over time, you get your rate of reaction. So guys, you see my formula for rate of reaction is always of what? It's always mass over time or volume over time, right? So this mass or volume is not fixed. It depends on the question. If the question is giving a product in a solid form, use mass. If your product at the end of the experiment is a gas, use volume. So basically just take mass or volume over time. That's the formula for your reaction. Okay, so you see, if I have a measurement for here, you see again it's mass, right? So I can use mass over time. Okay, but sometimes you might need to actually have this thing called the pressure meter. So pressure meter, I would say in your normal school, okay, in the normal SMK, they don't really actually have this device here. So it's not very important. But but if you think about it, let's say if I have a gas, I want to know whether the gas is actually getting more or less. I can just measure the pressure right now, because more gas means high pressure, less gas means low pressure. Okay, so basically this is something that we should know. Okay, and sometimes you can use electrical conductivity to find. Why? Because maybe before that there are actually ions. Let's say I have Cl minus, but after the reaction it becomes Cl2, covalent bond. No more ions. So means in the beginning, chloride ions, it is able to conduct electricity. Means in the beginning, you should see your light bulb or your ammeter is having a certain reading. But after you have the chemical reaction finish, no more ions, then the light bulb not gonna light up, the ammeter reading is 0. And that's when you know that your reaction actually stopped. Okay, if sometimes your ion will turn into covalent bond, then you can see the reaction stop. Or maybe in pH value, like I said, for neutralization. Okay, so I know we're gonna actually add acid and base together. Then when do I stop? When it's neutral, right? So we actually have your pH meter. So there are a lot of ways to measure the changes of a reaction. So the changes of a reaction is very important in terms of all this solid, liquid, and gas. But majority we use mass and volume. Mass of the solid, volume of the gas. Okay, so these are some just observational changes. Okay, some more examples here. This is from here. Okay, in this case here, we actually have the reactant. Okay, reacting with your maybe some liquid here, some solution here. But when this powder, solid powder, react with the acid or anything, they release out the gas bubbles. So the gas bubbles are here. I use a cotton wool and I try to actually let it flow out. Doesn't matter. Okay, but what happened is here in the beginning, the initial reading is in gram, 100 gram. After 2 minutes is 40 gram. Means what? Means that when the gas flow out, okay, means that the reactant is actually used up. The gas go out. The reactant getting lesser and lesser mass, right? So therefore we know that the mass decrease. Okay, so this is from 100, it turns into 40 after 2 minutes. For B is 100 turns into 80 after 2 minutes. Means what, guys? Means that we actually know that we're gonna do your calculation for rate of reaction. How do we do that? The rate of reaction I told you is actually the mass loss. Means how much mass do you lose before and after the reaction. So before is 100, after is 40. So you actually lost 60. And in 2 minutes, you lost 60 gram, right? So you take 60 over 2, you get 30 gram per minute. Means in 1 minute, this reactant lose 30 gram. Okay, but let's say if I have another experiment, which is 100 gram After 2 minutes, it turns into 80 gram. Means I'm going to take 100 minus 80, which is 20 over 2 in 2 minutes. You get 10 gram per minute. Means what? Means that in 1 minute, it loses 10 gram. So experiment A and B, they look the same, but probably something different in between the reaction there. You can see that the value for A is bigger than B, right? Therefore, rate of reaction is higher in A, lower in B. Okay, so that's how we actually normally find the rate of reaction of a certain experiment. So let's say if I have a gas, same thing, I'm going to actually have the initial volume and the final volume. So because at here, gas, the syringe actually at here should be in 0 in the beginning. After that, the gas will push, the piston will move out, move to the right. Then you can know how much gas collected. So because in the beginning is 0, so initial 0, 0. After 2 minutes, 40. After 2 minutes, 80. So in 2 minutes, he pushes 40, means in 2 minutes, in 1 minute, he actually had produced 20 cm³ of the gas. But for D, experiment D, in 1 minute, he produced 40 cm³ of the gas. So again, look at the number. Who is a bigger number? You can see that 40 cm³ per minute is larger than 20 cm³ per minute. Experiment D is a higher rate of reaction compared to experiment C. Means D can produce faster. Imagine D can produce 80 cm³ in 1 minute, but C only can produce 40 cm³ in 1 minute, or 20 cm³ in 1 minute. So you can see that the number gives you a very clear information about who is higher rate of reaction, about who is lower rate of reaction. Okay, so in conclusion, we are actually finding our calculation for today. So guys, today we need some basic calculation. So I will need your calculator out. Okay, so guys, you guys can pause your video here. Okay, prepare your calculator. Okay, so the first one here, you can see that average rate of reaction. Okay, there are two ways of finding rate of reaction. One way is when you actually see average rate of reaction. Whenever you see average rate of reaction, apply formula. Okay, so for this, apply formula. What's the formula for you to apply? Rate of reaction equals to mass over time or volume over time. Okay, so this is something I mentioned just now. But if you see instantaneous rate of reaction, means a rate of reaction at a given time. Let's say if my whole process takes 10 minutes, but I want you to find the rate of reaction specifically at second minute, at 2 minutes. How am I supposed to know? So therefore, for instantaneous rate of reaction, you're gonna actually have to draw graph. Plot graph to be exact. This one cannot sketch one. You must legit plot out the graph, only can do instantaneous rate of reaction. So let me just go through the first one first. How to find average rate of reaction? Let's say for here, I have a graph given to you. Okay, let's say I give you this graph here. Volume of gas, I have V1, V2, T1, T2. Okay, let's say for now, I want you to find the average rate of reaction from T1 to T2. So it means I want the reaction from here to here. You get a point? Means in between T1 here and T2, I don't want this. I don't want this. I only want this box. This L-shaped box. So how am I supposed to do that? So guys, basically finding rate of reaction is like finding gradient. Why? Because when you learn gradient in maths, if you remember gradient formula, it's y2 minus y1 over x2 minus x1. Okay, do you see there's a range? Same thing happens here is, you can see y2 minus y1 over x2 minus x1. So you can see v2 minus v1 over t2 minus t1. And that's when you want to find the rate of reaction in a certain range. Okay, now. But if you say, teacher, what if I just want to find the rate of reaction of the whole experiment? Very simple. You just take the final point. Okay, the point that you completely ended your reaction. Okay, take that x and y. You take y over x. Why y over x can straight away find the total rate of reaction? Because y over x is actually not a true formula. The legit point about behind y over x is, let's say if I say this is T3. T3, this is V3. T3 means at this point, do you see he started to become straight line? T3 and V3 is always at the point where you start to become straight line. Not at the back. Let's say for in the middle of here, cannot consider complete reaction. You must take the time where the line becomes straight line. So which is here. So if I have this T3 and V3, I have a total volume and the total time taken for the reaction to complete, right? So I'm just going to take this V3 over T3. You can find the total rate of reaction of this experiment. Because supposingly is to find the range of the whole reaction is V2, Y2 minus Y1 over X2 minus X1, right? But if you see this, you treat this as Y, you treat this as 2, you can see that the initial point is actually 0. Means that Y1 is 0, X1 also 0. So it's supposed to be like this. Okay, V3 minus V0 and T3 minus T0. But V0 is 0, T0 also 0. That's why we can simplify it becomes V3 over T3. So for rate of reaction, we call it the average rate of reaction. In a whole experiment, just take the maximum volume, divide the maximum time, and must be the point where it becomes straight line. Okay, cannot take the final time here. Must take the time when it becomes straight line. Okay, and it's very simple because you just have to apply formula. But for instantaneous rate of reaction, is where you cannot apply formula anymore. Why? Because to find a specific point, this average is to find the rate of reaction among a range. Okay, must be within a range. We call it average rate of reaction. But instantaneous rate of reaction means at that specific time in 32 seconds, in 54 seconds, at that moment of time, what is the rate of reaction? So we call that instantaneous rate of reaction. So how do you do that? So first, let's say if I ask you to find, guys, find me the rate of reaction at 38 seconds. So you go to 38 seconds, draw a dotted line goes up, then you draw a tangent line. So guys, do you all know what's a tangent line? So guys, no one is here to answer me. Okay, so tangent line means that a straight line that intersects with a curved line with only one intersection. So you see there's a straight line here, there's a curved line here. Do you see the intersect at here? So we call this the tangent line. And how to draw tangent line? Always draw your straight line, your straight tangent line, making some assumption. Okay, just like assumption, just assume a little bit that this area and this area. Do you see the triangle area, the pizza area? So the two area here, make sure you try to estimate them. Because some students will say, teacher, why not my tangent line like this? Why not my tangent line like this? Okay, now, so always find the best point to intersect with that point, with the time. Let's say my time is 38 seconds here. So go up 38, draw the best fit tangent line. How do I know the best tangent line? Always intersect at this point, at the time that you want. Then look at the area at the both sides. Try to have them at the same area, or probably you can use your protractor. Find the same angle. Okay. So just assume I don't need to really use protractor. Same area, same angle. Then you can draw down the dotted line. Okay, this triangle, the bigger the better. Okay, the bigger the triangle, the more accurate it can be determined the tangent gradient. So don't draw like this, so small. Who can see? So draw a bigger triangle. When you have this triangle, what you can do? Same thing. Do your gradient formula. You can treat this as coordinate number 1. Treat this as coordinate number 2, which is here I got x2, y2. Here I got x1, y1. So what you can do? y2 minus y1 over x2 minus x1. Find gradient. You can find you can see this rate of reaction. So basically, these two way of finding rate of reaction from the graph is the same formula, just that for average rate of reaction is to find within a range from T1 to T2. It's always given a range. While for instantaneous, there's no range, there's only one specific point. So you have to draw the triangle. Then you draw down the triangle already. You have the x1, y1, x2, y2, do your same formula for gradient. So I would say to calculate rate of reaction is not as hard as you think. It's quite simple. Okay, guys? So I will say that formula very simple. Okay, drawing graph also quite simple. Okay, from understanding here also quite simple. So I will say this is the first introduction of your rate of reaction. So guys, let's move on to our exercise. So for exercise, let me look at this. We're gonna go for page number 23. Okay, so let me drink some water. You guys just flip to page number 23. Okay, so what is the meaning of rate of reaction? Is basically you measure, number one, the change of quantity of your reactant or product, and you divide your time taken for your complete reaction. So therefore, it's a change in the quantity of reactant per unit time, or the change in quantity of product per unit time. So the keyword in the simple form is called per unit time. Okay, per unit time. And then number two, classify the following reaction as fast or slow. I believe this is very simple. Photosynthesis take hours, slow. Combustion, burn very fast, fast. Rusting, slow. Explosion, fast. So I'll say it's quite simple to understand. Number three, there are chemical reactions that are fast or slow in daily life. So again, let's try to arrange them in, okay, they want in the descending order, means from fast to slow. So who's the fastest here? I would say is combustion. Okay, so D is number one. Then I want something that is slightly slower. I would say it's your boiling eggs, C. After boiling it, something that is slower takes around like hours, I would say it's baking a cake, B. And lastly, probably take days, banana decaying, take months or take weeks, rusting of iron. So I'll say this is a very simple practice. Okay, but at here, you see number four, they say state the observable and the measurable changes. Means like what can you observe and what can you really measure to actually find your real reaction. So I mentioned to you guys, you got solid or gas. Try your best to actually measure solid or gas. Try to measure the mass, try to measure the volume. So let's say if you look at the first example, I have HCl aqueous, I have CaCO3 solid. I produce CaCl2 aqueous, H2O liquid, and CO2 gas. So what can you actually observe and measure? There are two things. Number one, among the reactant, I would say the solid very easy to measure, right? I can measure the using up of the CaCO3. How fast do you lose it? Okay, because you know you're actually using up CaCO3 to form all these things, right? So definitely CaCO3 will decrease against time. You can actually have the mass of it, or you can measure you can collect the gas. Once you have the volume of gas, you have the time, you can find your real reaction. So definitely the increase in the volume of carbon dioxide gas is one of the answer, or the reduction in mass of calcium carbonate. Either one of these, it's able to be used to find your real reaction. Okay. Number two, I have H2SO4. Oh, by the way, guys, because this is a recorded video, feel free to pause this video and write down your answer in your book. Okay, don't have to really ask me to wait for you. Okay, you can just pause this video. So B is H2O aqueous, Na2S2O3 aqueous. Everything else is aqueous, liquid, gas, and solid. In this case here, I told you guys, got solid, take solid. So the solid mass easy to actually measure. There's a gas here. There's no answer. Why not we measure the gas? Can also, but this gas is not very accurate. Okay, so for here, the best thing to measure is the formation of the precipitate, the mass of the sulfur precipitate. And lastly, you have both gas. You see, before reaction is gas, after reaction also gas. Can you measure any changes, right? Like previously is beginning no gas, after that got gas. Beginning no gas, after that got gas. So right now it's gas. So many gas. I cannot measure the difference gas, right? Because gas can slowly flow around. I said, teacher, what if I use a syringe? But a syringe is to collect the specific gas, right? But here, because you are having all gases here, gas can flow to anywhere. So the syringe not going to work. Probably the syringe caused by SO2, caused by O2. So the best way to actually measure when you have everything is gas is to measure pressure. Okay, means the reactor is gas form, your product also gas form. Then you really hard to differentiate the gas. So the best way to measure is to measure the pressure changes of the reaction. And lastly, I started off with ions, then turned into no ions, guys. Ions can conduct electricity, but H2O covalent bond cannot conduct electricity. So in this case here, we can measure the electrical conductivity or pH value. Why? Because this is acid, this is alkaline, this is neutral. Do you see pH value changing? Definitely, there are a few things that you can measure and actually see that, oh, I can actually find the rate of reaction of this experiment. Okay, so moving on, metals react with acid at different rates. Okay, metal with acid, you get salt plus hydrogen gas. Metal P takes 60 seconds, Q takes 95 seconds, and R takes 20 seconds. So definitely, I would say R is the most reactive metal because it only takes 20 seconds to react with your metal, right? To react with the acid. Oh, shorter time, higher rate of reaction. So what they want now is the time taken to collect 50 cm3, guys. The time taken here is for them to collect 50 cm3. Means R only take 20 seconds to collect 50 cm3 of gas. But Q takes 95 seconds only to collect the same amount of gas. So obviously we know P is the slowest, followed by, Q is the slowest, followed by P, followed by R. So calculate the average rate of reaction for each of the metal, means calculate PQR. Okay, so how do I do? What's your formula for rate of reaction? Volume, if you got volume, take volume. If you got mass, take mass. But because here it's collecting the gas, so take the volume of gas over time taken. So 50 divided 60, 50 divided 95, 50 divided 20. Try to do that. You will see values are provided. Okay, so you can see all this information provided. So based on your answer in A, arrange the three metal in decreasing reactivity. Means I want the most reactive one. So the most reactive one should give you the highest rate of reaction, means the highest value. So definitely it's R, followed by P, followed by Q. So therefore it's RQP. RPQ. I'm so sorry, RPQ. So in your conclusion, higher rate of reaction, the more reactive the metal is. So once again, guys, feel free to pause the video. I'm just going to move on. Okay, moving down. Question number 2, calculation practice. To practice your calculation, guys. So in an experiment, 60 cm3 of gas is collected in 40 seconds. What is the average rate of reaction? You have volume, you have time. Volume over time. Okay, so guys, when I say pause the video, let's say if you say, teacher, what if I say I want to do it myself, then only I check your answer? Can. So guys, you can pause the video before I show you the answer. Okay. So let's say now in question number 2, complete reaction between X gram of marble chips and nitric acid produce 42 cm3 of carbon dioxide gas in 3.5 minutes. Can you calculate the rate of reaction? Did they ask you to find X? Never, right? So the X probably is just there as a decoy to confuse you. So what they only want is the average rate of reaction in cm3 per second. Guys, always look at the unit. So that's why for here, 3.5 minutes is not suitable. I convert this into second by multiply 60. Then you take volume over this time. So guys, pause the video here because I'm going to show you the answer. Okay, so 42 over 210 seconds, you get 0.2 cm3 per second. Okay, so every time I will say like pause here, then you pause, then you do first, then move on to the next question. In number 3, calculate the average rate of reaction in gram per second. In this question wants you to have per second. So 0.5 gram given, nice unit also, but it takes it to completely dissolve in 80 seconds. So again in second, so gram per second, there is no need to do any unit conversion. Just take 0.5, which is your mass over time. So do you see why this question is mass over time? Because it is given to mass, right? Because the formula allows you to use mass or volume up to you, doesn't matter. Okay, so pause here. The answer is this, 0.5 over 80. Okay, next one, moving on. When 4.95 gram of reactive metal X is added to conical flask containing excess sulfuric acid, it takes 90 seconds for the reactive metal X to completely dissolve. Find rate of reaction in gram per second. I have 4.95 gram, 90 seconds. All the units are suitable. Guys, do it yourself. Pause here. The answer is this. Okay, which is the next one. It's something that you all learned before last time, just that you need to do it again. Of course, we're going to continue with our rate of reaction calculation. So let's just do a simple practice here. First, number 1, in an experiment, 3.6 gram of magnesium takes 20 seconds to react with dilute nitric acid. So first of all, to do this to find the volume of a certain chemical, to find a value of other chemical, always write chemical equation first. So I have magnesium, Mg, I have hydrochloric acid, HCl. So I'm going to plus these two together. So Mg plus HCl, you're going to get MgCl2 plus H2. The Mg displays off the H, becoming the H2 coming out. Balance equation, you get all this information. But then, guys, for those who used to be my students since beginning of the year, how to start this calculation? When I give you mass, and I want you to find volume of hydrogen gas, means the question wants you to find volume of H2, but I give you mass of Mg. So if I have mass, if I have volume, if I have mass, if I want to find volume, and these are two different chemicals, right? So how am I supposed to relate these two different chemicals? The only way to relate values or some numbers between chemicals, the only way to relate them is by number of mole. So always start with the information provided. Okay, for those who actually want to try yourself, you can pause it here first, do it yourself, then check my answer later on. Okay, for those who did not sure about it, let me just go along. M equals to 3.6, right? Because I have mass given, the formula given to you guys. What is the number of mole formula that contains mass? Is mass over molar mass. So I'm going to take 3.6 over the molar mass of Mg, which is 24. Okay, it is not given by the question. Oh, guys, it's here. Relative atomic mass is 24. So you can just put in 24. You should find the number of mole of your Mg. But that is only the value for Mg. Nothing relate to H2. But what you really want is H2, right? How am I supposed to relate Mg to H2? You always have a step 2. That step 2 is looking at the ratio in your equation. What's the meaning of it? If you look at Mg, is there any number in front of Mg? No number means 1. H2, again, no number means 1. So means the ratio in your equation between Mg and H2, the ratio between Mg and H2 is 1 to 1. Therefore, if my Mg is 0.15, your H2 number of mole also 0.15. So what we are trying to do here is, I cannot find the number of mole of H2. The only way to find the number of mole of H2 is by finding this value, compare the ratio. Okay, so therefore, from the equation, 1 mole of Mg produce 1 mole of H2. So 0.15 Mg produce 0.15 mole of H2. So what's the purpose of finding this? Why do we need to actually find 0.515 mole of H2? That's a number of mole of H2, right? Very obvious, because I am having number of mole, I want you to find volume. And then do you see they mentioned to you room condition? So for those who remember, what formula from number of mole can use room condition, can use STP? So we're going to call that number of mole equals to volume over molar volume. So therefore, I'm going to use that as my last formula. I have my number of mole of H2. I have my molar volume given by the question, 24. Okay, so I'm going to bring my 24 over, multiply 0.15. I get my volume of H2 gas is 3.6 dm cubed. And that's how we actually find a value for a chemical when they give you something else. Okay, you see, a question gives you 3.6 gram of Mg, but at the end they want you to find H2, right? So the only way to relate two different chemicals is by your chemical equation, the ratio, the number of mole of them. Okay, so find the first information, compare number of mole, then you can apply your final calculation. So for those who are actually not sure how to do this in details, I have a YouTube video about that topic. So please feel free to go along with that. Okay, I'm not going to stay here for too long. Then based on the volume of gas, so means I found the volume of H2 in the previous question. Can you calculate real reaction in dm cube per second? Means you produce 3.6 dm cube of H2 in 20 seconds. Do you see it gives you time for a reason, for you to do B? So therefore, I'm just going to take 3.6 dm cube over 20 seconds. The units already matching up, dm cube and second, nothing to change. So you have 3.6 divided by 20, you get 0.18 dm cube per second. And that is that's the value for your average real reaction. Okay, so for those who want to pause here, I'm going to move on. Okay, do the same thing, guys. Okay, I have this thing called a calcium carbonate. Okay, it's added to your hydrochloric acid. So calcium carbonate is CaCO3, hydrochloric is HCl. Do your chemical equation, you get CaCl2, CO2, and H2O. Balance equation. Okay, now again, I give you 50 cm cube, this is volume. I give you 0.2 mole per dm cube, this is your molarity. And that's for acid, means I have the information for acid. But the question wants you to find what? What is the maximum volume of CO2 gas? Means the question wants you to find this. So I got volume 50. I got concentration, or known as molarity. So how do I start? Always start with the chemical with information. Means I have V, I have MV, right? So for those who follow me throughout the class, I have molarity, I have volume. How to find number of mole? We have the formula called MV over 1000. So I'm going to use MV over 1000, find the number of mole of HCl. Furthermore, I'm going to continue on ratio comparing. So before I say this, can I use this in my final formula? Cannot, because this value found is for HCl. So better compare first. So 2 HCl give you 1 CO2. So the ratio is 2 to 1. So if HCl is 0.01, means your CO2 must also divide by 2, because 2 become 1 is divide 2, right? So it means it's going to take this value, also divide 2. Then you get the number of mole of carbon dioxide. So therefore, my calculation in this way, and there you go, you found your carbon dioxide number of mole. Once you have a number of mole of carbon dioxide, can you find volume? Okay, can you find volume? And they say room condition, right? If I have room condition, means V over MV, which is the molar volume formula. So I'm going to bring my formula 24 molar volume over the number of mole, multiple number of mole. You're going to get 0.12 dm cube, but they want you to find it in cm cube. So convert from dm cube to cm cube, you times 1000, you get 120 cm cube as your volume of carbon dioxide gas produced. Once you produce your CO2, what is your average rate of reaction? How to find rate of reaction? Volume over time. Volume found it, but what's my time? 180 seconds. So 120 divide 180, 0.6667 cm cube per second. Some student might ask, teacher, can I able to use 0.2 over 180? Sure, but the unit will become dm cube per second. It depends which one you use. Go according with your unit. Okay, and next one, question number 7. Guys, pause here if you want to. Question number 7, you have your find the overall reaction, the average rate of reaction. You can see from here, you see time going across 1 minute, 2 minutes, 3 minutes, 3.5 minute. The volume of gas given to you. Do you see the volume of gas at one point? It stopped increasing. Do you see at 14.5 it becomes straight line already? It becomes constant. Means what? Means that you are not having any gas coming out. Means that your reaction is completely reacted. Means the reaction is completely finished. Okay, so if you want to find the overall rate of reaction, what did I told you? Take the maximum volume, which is 14.5, but over the time, not total time, is the time where your reaction stopped. The first point where your reaction stopped, which is this point. Not this point. So it's 14.5 divide 2.5. You get 5.8 cm cube per minute. But in the first minute, how to find it? In the first minute means I'm going to go to first minute minus of the initial minute. Okay, so I'm going to take, okay, same thing, still volume over time. So 7.5 minus 0 over 1 minus 0. So 7.5 cm cube per minute. So why do I minus the first value? Because I told you average rate of reaction means a range. Even though the initial point is at 0, it is quite important to write this down like 7.5 minus 0, 1.0 minus 0. That is the way to actually let your teacher know I'm trying to do average rate of reaction. Okay, if you never minus something, then you know that it's not average rate of reaction. Next one, in second minute. So in second minute means, right, in this second minute, from first minute to second minute, So what happened is, you see that I will take 12.5 minus 7.5, 2 minus 1. Why do I minus this point? Because this question C is want you to find the rate of reaction in the second minute only. You get the point? Okay. In the second minute only means I don't want to include the first minute. I only want the second minute. So I take my second minute info minus off the first minute info. I can find the value in the range. And that's how I do it. Okay, for guys, those who want to copy down or do it yourself, pause there, pause here. Okay. Next one, pause it if you want to try it yourself. But I will just go on with it. So in the first 30 seconds, very simple, first 30 seconds, volume over time. So 7 over 30. In the first minute, means 60, from the first point to the 60 seconds, so 14.5 over your 60. In the first 2 minutes, guys, do you see a difference here? First 2 minutes and in second minute is totally different thing. First 2 minutes means including the first minute. Means from initial all the way until second minute. Until 2 minutes. So I'm going to take 100, your 26.2 over 120. That's your rate of reaction in the first 2 minutes. But if you only want in the second minute, means you're going to minus off your first minute. So I'm going to minus off first minute. It's here until here. So 26.2 minus 40.5, 120 minus 60, you get your answer. From 90 to 120, from 90 here to 100, to 120 is here. Just do your maths. Okay, 120, 6.2 minus 20.5 over 120 minus 90, and you divide it, you should get your value. So I would say average rate of reaction is always within a range. Okay, always in a range. Okay, even though if they say like first 30 second, first minute, first 2 minutes, your initial point is 0. Okay, so now I have 3 experiments here with different steepness, but they all reach at the same height. So what we know is calculate the average rate of reaction for experiment 1. How to calculate rate of reaction? Average. So I told you, if they never give you table, try to find the point from the graph. So in experiment 1, try to find the point where you start to become straight line. I will say it's around this point. Okay. Then for experiment 2, it starts to become straight line. I will say around this point. Experiment 3, it starts to become straight line. I will say around this point. So it's at 20 seconds, 30 seconds, and 55 or 56 seconds. So it will be the answer will be having a range here, guys. So don't have to be very exact. So, but then do you see the volume of gas of them? They're all the same. They're all having 50 cm3. So 50 over the first experiment, 50 over 55 or 56. You see, I put here 55. 56 also correct, doesn't matter. They have a range for your answer, don't worry about it. Experiment 2, it's 30 seconds. So 50 over 30. Experiment 3 is 20 seconds. So 50 over 20. So they see volume will never change, but time change, right? So who give you the largest value? The largest rate of reaction? I will say the largest number. C is the highest rate of reaction. Okay, pause here if you want to copy down. Okay, moving on. Another graph. Calculate average rate of reaction for the overall, guys. Overall means, again, maximum volume over maximum time. But the time must be the time where you start to become 0, not the legit total time. The time when you stop reaction, that's your total time. So volume maximum, I will say around 35, 36. Then the time to become straight line is around 300 seconds. So I will say 36 over 300. You see? First 3 minutes means first minute, second minute, third minute. Okay, so for third minute means like they want the final point until the first point. So take this as x2, y2. This one is x1, y1. Okay, just do your gradient formula. Okay, so you can see that why is it 30? Because it's actually 30 In the first 3 minutes, oh guys, so I'm so sorry. First 3 minutes is here. Hey, I'm so sorry, guys. sorry. Yeah. So for the first 3 minutes is 180 seconds. So for here, according to your graph, your volume is around 30. So they take 30 over 180. That's your value. In the third minute, guys, when you see it in the third minute, means you cannot use a range formula anymore. You must actually draw a tangent line. So draw a tangent line. No. In the third minute, guys, still in the range because still average rate of reaction. Third minute means I don't want to include first and second minute, so I only want from here to here. Okay, I need to minus off first minute, I need to minus off second minute. So in total, just minus off second minute. Means like finding the area under here, I don't want this, I only want this. Okay, so how do I do that? Take this, volume 30 minus 25. That's a value for second minute. Okay, so 30 minus 25, then 180 minus 120. And there you go in the third minute, means excluding first and second minute. Okay, and slowly going down, you have your average rate of reaction. For this, you can see overall, again, find the maximum volume and the time where you stop. Okay, when you see the word overall means maximum volume and the time where you stop. So maximum volume around 33, that's a volume for the gas collected, 33, and you stop around this point. And that's the time at 240 seconds. So 33 over 240. First 3 minutes is 180 seconds, which is here. Okay, which is around 31 over 180, 31 over 180. From 90 to 150. So from 90 is here, 90 is here, 150 is here. So do your maths. Take the bigger one minus the smaller one. Y2 minus y1 over x2 minus x1. Pause here if you want to. Try yourself. So 30 minus 24. Why here? Because here is 30, here is 24. That's the volume difference here. So 30 minus 24, 150 minus 90. Okay, pause if you want to. Continue down. Okay, based on the graph, this is actually a drawn tangent line with a triangle. Everything is drawn to you. So because in online class we cannot guide you along with the drawing of graph, so just let's assume that you guys can draw tangent line yourself, So can you calculate the average rate for overall reaction? So we see the word overall, maximum volume over the time where you stop. So maximum volume is 80. The time where you stop is here. Okay, so I would say it's around like 210. So 80 over 210. But now B onwards, they say rate of reaction at 60 seconds. Do you see this is a specific number, specific time? And there you have to actually draw a tangent line. So you have to go to a 60 second there, draw a tangent line. Do you see this tangent line? Okay, do you see the label for you also? The tangent line is actually 102 minus 18 and 68 minus 24. You see that? Means this is y2 minus y1. This is x2 minus x1. So since I give you this value, just take this over this. 64 minus 20, 68 minus 24 over 102 minus 18. You get your reaction at 60 seconds. Lastly, instantaneous rate of reaction at 90 seconds. Again, instantaneous, go to 90 seconds. Plot tangent line, draw your triangle, get your y1, y2, x1, x2, y2, get your x1, y2, x1, y1. Then you try to find the difference in y, difference in x. So do your same formula, y2 minus y1 over x2 minus x1. So you should get all these values. Okay, so guys and girls, I'm going through a very fast way because this is a recorded video. There's no interaction between anyone. So feel free to pause within all the videos, okay? So I will say that's all for this class. I will keep this video on YouTube permanently. so that everyone can come back to this revision on YouTube. Okay, so I will set this as a compensation for this week. Okay, I'm so sorry for the last minute cancel class. Okay, so guys, I will see you next week.